So recursion is actually not specific to programming. It's actually very common in mathematics, but it's called induction in math. For example, the most common one we know is the Fibonacci sequence. If you've never heard of the Fibonacci sequence, the sequence goes like this. I think it starts with 0, then 1, then 1, and then 2, 3, 5, 8. If you've never seen this sequence, it might be a little bit puzzling how you come up with this sequence, but we'll talk about that later. And then the next number, I think it's 13. So that's the Fibonacci sequence. And essentially, if you haven't figured it out already, the key is that your number is the sum of your previous two number. So for example, 3 plus 5 equals 8, 8 plus 5 equals 13. So this is the proper definition, the mathematical definition. Basically what it's saying is the same thing as what we said before. We are saying that f of 0 will be 0, f of 1 is 1. So these are like the base cases of your sequence because it has to start somewhere. And then here it's saying that the function with argument n will be f of n minus 1 plus f of n minus 2, meaning what we said last time, which is just the sum of your previous two numbers. So I guess in some ways, if we're talking about functions, this is the same as saying f of 0 will be 0, f of 1 will be 1, and then f of n, where n is a variable, it will be equals to f of n minus 1 plus f of n minus 2. Same thing. All right, now let's try to solve for f of 5. And, I don't know what f of 5 is on top of my head. So we have our equation here on the side to remind us what Fibonacci sequence is. And then we'll just solve for 5. And we'll do this so that we can understand how to translate this into code later. So what's f of 5? Okay, so I will replace n by 5 over here. So is this f of 5? No. Is this f of 5? No. This is f of n. So let's replace this by 5. So it's f of 5. And then because n equals 5, this will become 5 minus 1, which is f of 4. And then this will be 5 minus 2, which is f of 3. Okay, so I guess we have that. So we have f of 4 plus f of 3. Great. But the issue is we don't know what f of 4 is, nor we know what f of 3 is. So what do we do? Well, it's okay. We could just continue doing that. So instead, maybe you could have replaced n by 4. So it would have been f of 4 equals to f of 3 plus f of 2. So this would be f of 3 and then f of 2. Same thing here. This will become f of 2 plus f of 1. Now looking at all these, we still don't have the answer except for f of 1, because here it says explicitly that f of 1 equals 1. All right, let's just put 1 here for now. And then we'll continue with the other ones. F of 3 equals f of 2 plus f of 1. And then f of 2 is f of 1 plus f of 0. Okay, and then here's the same thing, f of 1, f of 0, right? Simple stuff, f of 0. And then here it's only 1, so we got it. So then what can we replace? We can replace f of 0, which is 0 in this case. So here it would be 1. This becomes 0. This becomes 1. F of 0 is 0. F of 1 is 1. F of 1 is 1. F of 0 is 0. F of 1 is 1. Okay. And now it's starting to make sense, or at least it's starting to have values instead of variables, or instead of the functions. So which is great, because now you know f of 2 is equal to the sum of both of these numbers. So 1 plus 0 equals 1. So now we can replace f of 1 by 1. And then same thing with f of 3. What's f of 3? It's 1 plus 1 now. It used to be f of 2 plus f of 1, but now that they're turned into numbers, I can actually add them. So this becomes 2. All right, we're done with this side. Let's go on this side. Okay, f of 2. F of 2 is 1 plus 0. Okay, we got 1 here. All right, so now we have f of 3 equals 1 plus 1, so that equals to 2. F of 2 here equals 1 plus 0, that equals 1. And then f of 4 is equal to 2 plus 1, so that's 3, okay? And then f of 5, what is that? It's 3 plus 2, so f of 5 equals 5. And then if we look at our previous slide, see if we are correct. And then the sequence we have is the 0 number, the first number, second, third, fourth, and fifth. And the fifth number is indeed 5. All right, Perfect. So what we could have done before is that we also know that f of 0 is 0 and f of 1 is 1. And then once we know what f of 2 is, because f of 2 equals f of 1 and 0, we could just look back and then we know that that's 1 because it's the sum of f of 0 and f of 1. And then whenever we got new information about the f's, we just write it down here. And then it will help us complete all the way up to f of 5. All right, cool. So how do we write this in code? Pretty simple, because you should just use this. This is basically your function, and just write that, but in terms of code. All right, let's whip out REPL. So remember what we had? We had f of 0 equals 0, and f of 1 equals 1, and also f of n equals f of n minus 1 plus f of n minus 2. All right, so let's define a function called fib for Fibonacci and give it the integer n, or give it the parameter n, which is an integer. And then we literally just copy this, but in code form. Okay, we have an if statement. If n equals 0, then we return 0. And then else if n equals 1, I had a typo here, fix that typo. And then if it's 1, it's equals to 1. And then if else, meaning if n is bigger than 0 or 1, then we know it's f of n minus 1 plus f of n minus 2. So how do we define that? What we can do is literally do the same thing. So f, or fib, is this function. And then what are the parameters? It is n minus 1 plus Fibonacci n minus 2. All right, let's run this and see if it works. So remember what 5 was? If we give it 5, it should give us 5. Excellent. So then 0. Okay, excellent. Okay. And then what we can do is for I in range, where do you want to go? Let's go all the way to 10. Okay, I want to print Fibonacci I. So what I'm doing here is I'm looping from 0 to 10, not including 10, and then I'm just going to print what the number gives me for Fibonacci. Oopsies. Let me do that again. Add a little tab, Fibonacci I. All right, so yeah, so that seems like the sequence that we want. And I think, yeah, that's pretty much correct for the Fibonacci code. So we wrote 2 recursive functions so far, one in the previous lesson and one today. Most of the time, recursive functions have 2 cases. I'm not sure if you noticed by now, we have something called a base case, and we have something called a recursive case. So what that means is the base case, which is the smallest instance of your problem, and you know the answer already. So that's what a base case is. For example, in our case, it's f of 0 equals 0 and f of 1 equals 1. These are the base case because you don't need to compute to know these answers. This is like the easiest answer you can get from that problem, and the problem meaning solving for function Fibonacci. And then for recursive case, the recursive case allows you to solve your current problem by assuming you know the solutions to slightly smaller problems. So for example, if I want to solve f of 5, then I assume that I know what f of 4 is and I know what f of 3 is so that I can solve f of 5. Because if I know what f of 4 and f of 3 is, then I know I just have to add them. And then this translates in general to f of n equals f of n minus 1 plus f of n minus 2. This is the recursive case, and then these 2 are the base cases. This is the base case, these two if and else if statements, and then this is the recursive case. So remember last time where if we remember when we removed a base case, we actually had an infinite loop, or like a Stack Overflow, right? And here we have a base case that prevents us from looping infinitely. But in here, we recurse infinitely. So we know that Fibonacci is basically adding the 2 previous numbers together, but we always have to have a base case is so that your Fibonacci can actually be able to solve the problem by itself at one point. Like for example, if I took this off, the base case, and I only had the recursive case, then what would happen is that it would recurse infinitely. So 5, yeah. Line repeated 996 more times, maximum recursion depth. You will see this if you make this mistake. So remember, always think of the base case And then think of the recursive case. Very easy way to write recursive functions is to understand what are the easiest case, and then you write them down. And then in the recursive case, pretend that you already have your problem solved for smaller instances. And then assuming you have those solved, how would you solve your current case? You could, for example, replace n by 5 in your mind and say, okay, well, what is Fibonacci 5? Well, it's Fibonacci 4 plus Fibonacci 3. So yeah. And then to summarize, recursion is a method of solving a problem where the solution depends on the solutions to smaller instances of the same problem. So for example, in our case, in Fibonacci, F5, that's our main problem. This is the problem that we're trying to solve. And then it depends on the smaller instance because this is f of 4, 4 is smaller than 5, f of 4 and f of 3, these are the smaller instances. It depends on the solution of the smaller instances, which is f of 4 and f of 3 of the same problem. And it's the same problem because there are both f's, which is the problem of Fibonacci. That's pretty much it. And by the way, you can actually write Fibonacci with a while loop. So you can try that yourself. It's actually also more efficient, but we won't get into efficiency until future courses. All right, that's it for now. I'll see you next time.